So we are going to continue with the afternoon session. So the next panoramic talk is by Genia Tevelev from UMass, and a little bit Chilean. It's called Semi-Orthogonal Decomposition of Fano Varieties.
Thank you, Alvaro. Thank you for the invitation. It's great to be at ELGA again. So in my talk, I will be talking about smooth projective varieties over field of complex numbers, but I will try to break them into simpler pieces, as this kind of a diagram indicates, and then these blocks will kind of fly inside our variety, and sometimes they will reassemble in various interesting and fascinating ways into other projective varieties. So it's very much a developing field. There are many fascinating conjectures inspired by mirror symmetry, by Bridgeland stability conditions, by rationality problems, and other things. So I'll try to get to some of my results in some specific examples. But if I want, then they're in these three papers. One of them is in collaboration with Sebastian Torres, who is here. Another one is in collaboration with Elias Sink, who is at Harvard. So I should probably tell you right away what this semi-orthogonal block is, but maybe it will be better if I try to motivate the definition a little bit before I get to it by looking at sort of the simplest possible example. So let's take E to be a vector bundle over Y. So again, all of my varieties will be smooth projective varieties, so I won't be repeating that. And let's take X to be a projectivization of this vector bundle with a map pi back to Y, so that a fiber over each point is a projective space of some dimension. Then it's very non-controversial that X has Y as a block. For example, by a well-known formula, if you take a cohomology of X over rational numbers, then it's essentially the cohomology of Y over rational numbers, and then you adjoin a variable, and then divide by the Chern polynomial. Right, so additively, cohomology is just built from R+1 copies of cohomology of Y, and then the multiplication kind of tells us how these blocks interact with each other. And there are similar decompositions in Chow groups, in motifs, etc., but I would like to make it as geometric as possible. And so to make it geometric, well, somehow I have to send Y back into X. And where can I possibly send Y? So if I take maybe some point of Y, well, I can only send it to the fiber, right? Where else? I can send it to the fiber over that point. But then the question is how to think about this fiber, because there are various ways. So classically, maybe one wants to think about this fiber as a point on the Hilbert scheme of Y, which parameterizes all subvarieties and subschemes of X. And it's actually kind of a reasonable thing to do, because an easy exercise will convince you that this turns Y into a connected component of that Hilbert scheme. So we can kind of reconstruct Y from X as the moduli space of these rulings of the projective bundle. And so maybe then very naively, we should think about blocks of X. So now X can be any smooth projective variety as moduli spaces of some objects on X. Right, but there are, of course, two problems with this. One is that typically a moduli space is much more complicated than X, and we want Y to be simpler than X. So there's one issue, so it must be simpler than X in some way. Right, but then there is a bigger problem, that we want our blocks to kind of interact with each other. And typically, when we deal with moduli spaces, blocks, these different moduli spaces, they sort of live in different universes, and they don't interact with each other. So we should somehow put all of these moduli spaces into the same kind of ambient universe. Right, so well, let's rethink this process then. So where else can we send y? So if we take a point again on y, then instead of sending it geometrically into that ruling, we can send it into the structure sheaf of this ruling. And of course, I have to put the structure sheaf of the ruling back onto X. So if my embedding is I, then classically what you do, you just push it forward back into X, and then this becomes an object in the category of coherent sheaves on X, right? So now this looks like a really weird procedure because we start with a complex point on a variety, but we send it to an object in the category, right? But it's not as crazy as it looks, because if you think about it, all we do is that we take the category of coherent sheaves on Y, vector bundles and things like that, and then we just take a pullback functor into the category of coherent sheaves on X, right? And then, well, if you take a skyscraper sheaf of a point on Y, then its pullback will be this sheaf over here, the push forward of the structure sheaf of the ruling, right? So it's not so bad. Now we have two categories: coherent sheaves on Y, coherent sheaves on X, and the pullback functor. So now this is sort of a talk about categories. So whenever we talk about categories, we have to remember not just the objects, but also all the morphisms. So we can ask, well, what kind of properties this functor has? And sort of an easy exercise, right, is that this functor pi upper star has the easiest possible effect on Hom spaces. It actually preserves all Hom spaces, right? So this is called a fully faithful functor. Right, so for example, if you take two different rulings, or maybe the same ruling, and you compute the Hom, from I lower star of one ruling into I lower star of a structure sheaf of another ruling, right? So then you're going to get the same thing as just Hom from Kx from one skyscraper sheaf into another skyscraper sheaf. So it's going to be C if X is equal to Y, so this is a simple sheaf, and 0 if X is not equal to Y. Right, so if you read Hartshorne, you already solved this exercise in your head. Well, if not, there is a hint to this exercise, right? So the reason this works is because the push forward of the structure sheaf on X is equal to the structure sheaf of Y, right? Which is equivalent to pi being a contraction from, which were defined in Cinzia's talk. So it's the same condition. Pi is a contraction. It's a morphism with connected fibers, surjective onto the normal base. And so then it looks like we solved the problem, because now we are in this world of contractions and faces of the Neff cone and all that, like Mori theory. But now if you think about it, we actually did this sleight of hand that now instead of rulings, we talk about these sheaves. And what happens in the process is that we lose the moduli space interpretation. So here's the non-example. Maybe I'll actually save this here and do it on the other side. So here is a non-example. So instead of taking this kind of irrational fibrations, let's take an elliptic fibration. So that for some point, the fiber is an elliptic curve. Right, and so then if we do the same thing, if you take the push forward of the skyscrapers of the structure sheaf of the fiber, then actually there are two different directions how it can deform. It can deform into the push forward of the structure sheaf of another fiber. When we deform X to Y, these sheaves deform. But there is a different direction, because we can also deform to the push forward of some other degree 0 line bundle on the elliptic curve. Okay, so we lose this interpretation of the base of the vibration as the moduli space. In fact, if you think about what the moduli space of this structure sheaf would be, it will actually give you sort of the same elliptic vibration back, or rather like a Jacobian elliptic vibration back. So we have to kind of modify the definition a little bit. So this is not enough for our purposes. So now, let's go back to the this projective bundle picture, and let's ask, okay, but then what else do we have in this example, which we don't have in the elliptic vibration example? And as it turns out, sort of the beautiful thing about the projective bundle situation is that we not only have the matching of Homs, but we also have the matching of X groups. So if you take xi from the push forward of the structure sheaf, I'll just do it for one point, so PRY into the push forward of the structure sheaf, maybe at the same point, then you will get the same thing as xi from from the skyscraper sheaf into itself. So this functor matches not only Hom spaces, but also all the x's between the sheaves. And so, for example, well, maybe I should have used I, let's use j. So for example, if j is equal to 1, then this X1 group exactly parameterizes infinitesimal deformations of the sheaf. Right, but on the other hand, well, if you compute X1 from the skyscraper sheaf into itself, you will get exactly the tangent space to y at the point y. Right, so we see that this structure sheaf of the fiber has the same deformations as the point on the base. So now this is great. Well, and if you want to solve this exercise, so it's another exercise, then the hint for that would be to use a little bit of a stronger property. So as it turns out, that for the projective bundle, not only the push forward of the structure sheaf is the structure sheaf, but there are no higher derived push forwards. Right, which is a much stronger property than just being a contraction. Right, and so somehow we want to maybe understand this a little bit better, right? So we want to understand not only Homs, but also X spaces. But it's kind of nice to have this interpretation that the functor is fully faithful and we are done, right? Just a fully faithful functor between categories. But fortunately, this actually can be done in general we just have to enlarge the category a little bit. So instead of talking about the category of coherent sheaves, we have to switch to the derived category of coherent sheaves. So if you don't think about derived categories every day, so here is a little bit of a kind of a cheat sheet about them. Right, so on one side, well, we have this coherent sheaves on X. And so then what are the objects in the category of, in the derived category of X? Well, those are just bounded complexes of coherent sheaves. And there is a very simple way to embed coherent sheaves into complexes of coherent sheaves. Well, you just take a complex which is concentrated in degree 0. Right, so when you start to study derived categories, it's kind of a tricky and it takes a little bit of a work to define morphisms in derived categories. But instead of doing that, let me tell you a few things about the properties of these morphisms, because that's really what we want. So one thing is that we can shift a complex. We can take a complex and just shift it to the left. This is called the shift functor. So this will also be defined on morphisms. And then sort of a remarkable thing happens. So one is that if you want to compute the Hom between two coherent sheaves, you can also compute the Hom between the corresponding complexes. So we don't lose any information about Homs of coherent sheaves. But even more remarkably, if you want to compute X between two coherent sheaves, what you can do instead, you can shift one of them by I and then just compute the Hom. So in other words, not only Homs, but also X between coherent sheaves are completely encoded in the Hom spaces in the derived category. So another very useful thing is that in algebraic geometry, we like resolutions. So for example, if we have a line bundle or a vector bundle and its section, which vanishes in the right codimension, so the codimension of the scheme of zeros is exactly the rank of a vector bundle, then we have this famous Koszul resolution of the structure sheaf of Z pushed forward into X by exterior powers of the vector bundle. But in the world of derived categories, things are even better. So in the world of derived categories, while this coherent sheaf supported on Z is just isomorphic to the Koszul complex. And in fact, any complex of coherent sheaves is isomorphic to a complex of vector bundles. So we can just work with vector bundles to compute whatever we want. So another remark is that sort of the category of coherent sheaves is what's called the... Oops. So here Z is this vanishing locus of a section. Yeah, and this gives this resolution. Right, so another remark is that the category of coherent sheaves is an abelian category, which means that we have a notion of a short exact sequences and various axioms. The kernel of the co-kernel is isomorphic to the co-kernel of the kernel and all that. So the derived category is not abelian, it's what's called a triangulated category, which means that there are this kind of a special sequences when we have a Hom from F to G to H and then from H to F shifted by 1. And there is a certain distinguished class of this triangle called exact triangles or distinguished triangles in some books, which again satisfy various axioms. And these axioms are even better than axioms of the abelian category. Like for example, if you have any Hom from F into G, there is a unique way to extend it to this exact triangle of this form, where H is called the cone of the morphism from F to G. And actually, even if you start with 3 sheaves and an exact sequence of sheaves, there will be and then you just think about F, G, and H as objects in the derived category, you will get the corresponding exact triangle of this form. And if you're curious, what is this morphism from H into F in this case? Well, if you have a short exact sequence, it is defined by, it is defined by some x1 from X into F. And we have already seen that to have a Hom from F to G shifted by 1 is the same thing as to have x1 from F into G. And so that's the map from H into F that you get. And finally, well, if you have a morphism of smooth projective varieties from X to Y, then as always, we have various functors. We have a push-forward functor, the pullback functor on coherent sheaves. And we have the corresponding functors between derived categories, the derived push-forward, the derived pullback. And again, well, even if you primarily are interested in coherent sheaves, there is a relationship, right? So if you take a coherent sheaf and you push it forward as an element of derived category, you will get some complex of coherent sheaves. You can take cohomologies of that complex of coherent sheaves, and they will compute Hartshorne style, high derived push forwards of that coherent sheaf F. So kind of things become much simplified. Okay, and so with this I can give a definition. Right, so we say that Y, as always, a smooth projective variety, is a semi-orthogonal block of X if there exists a fully faithful functor, so the functor preserving Hom spaces, from dby to dbx. And sort of this example that we studied can be generalized a little bit. So if we have any morphism f, from x to y, which has the property that the derived push forward of ox is oy, and examples of such morphisms are, of course, abundant in geometry, especially geometry of Fano varieties. So x can be a projective bundle over y, or for example, f can be just any birational morphism. So what else appeared in Cynthia's talk? A conic bundle. Right, so in all of these cases, this is the case, and so we see that in all of these cases, we will have this functor, and the functor will be just a derived pullback. So LF upper star from dby to dbx will be fully favored. Right, so we have blocks given by sort of classical birational geometry, but of course the beauty of the subject is that there are blocks of a completely different nature. For example, let's say we want to cook up a fully faithful functor from the derived category of a point, right, to the derived category of x. Okay, so then, coherent sheaves on the point is the subject of linear algebra, right? So vector spaces are, linear algebra is an algebraic geometry of a spectrum of an algebraically closed field, right? Yeah, and so, it's trivial, as my back says, yeah. And so then, so this category has an obvious generator, just one-dimensional vector space, right? And, well, I mean, it's an exact category, right? So xi, from k to k is equal to c if I is equal to 0, and to 0 if I is not equal to 0. Right, and so then, if you want to cook up a functor like this, right, so then this k has to go to some object E in the derived category of x, maybe to a vector bundle or to a complex of vector bundles. We should have exactly the same home spaces. And while these objects appeared in Giancarlo's talk, right, so E must be an exceptional object. Right, so x between it, x of it with itself, should be the same. Right, so we can think about exceptional objects as points, point type kind of blocks inside our variety. Any questions? Okay. So it would be nice to get some kind of a characterization of these blocks on X without referring to Y, and this can almost be done. So those are these admissible subcategories. So let's again take this derived category of X, and let's look at the full triangulated subcategory. Full means that, again, we are taking all possible homes between objects within A. So then this category is called admissible if it admits a right adjoint functor, sort of sometimes also called a projector function from dbx back to A. So like an innocuous definition, but in fact, these guys are very rare. And this condition is equivalent to a different condition. Right, so this happens if and only if the derived category of X admits a semi-orthogonal decomposition, or SOD. And so what does this mean? So this means that actually there are two subcategories, not just this A, but also there is another category B, also a full triangulated subcategory with two properties. So there are no homes from right to left, so no homes from objects in A to objects in B. That's condition number one. And then the condition number two is that every object in the derived category of X can be obtained as a sort of an extension of an object from B by an object of A, or technically speaking, there exists this triangle, which will necessarily be unique, which has T in the middle and connects A to B. So you can think about this as sort of an extension of B by A. Right, and so then in our situation, right, when we have this fully faithful functor from dby to dbx, it's actually a fact, well, it's a sort of a combination of many various famous and hard theorems in the study of derived categories, that the image of the derived category of y will automatically be an admissible subcategory in the derived category of x. So admissible subcategories of this form obtained using fully faithful functors from the derived category of another smooth projective variety are called geometric, right? Because as we will see, not every admissible subcategory actually shows up this way. And another thing I want to say is that one can, of course, iterate this process. So instead of just taking sort of a two-step semi-orthogonal decompositions like here, one can take semi-orthogonal decompositions with many steps, and the definition will be the same. So they will all be full triangulated subcategories. There will be no horns from right to left, and there will be an analog of this sort of filtration property, but one would have to take sort of iterated extensions to actually get any object in the derived category of X. Okay. So maybe a quick example of a semi-orthogonal decomposition. Well, actually, we were talking about these projective bundles, so that's one example. So this is something called the Orlov projective bundle formula. So if X is a projective bundle over Y, right, so then the derived category of X will have a semi-orthogonal decomposition into R+1 copies, where R is the rank of the projective bundle of derived categories of Y. Where R is the rank of the projective bundle, or in other words, as many copies as the rank of a vector bundle. And if you're curious what are the functors, right, so we have to cook up some kind of functors from dby to dbx. Right, so we already saw that just taking a push forward, the pullback works. Right, but we need more, right? We need R+1 functors, but we can do a very simple-minded thing. We can just tensor this with a relative line bundle that we have on any projective bundle. And so I here has to go from 0 to R. So we'll get as many blocks as we have, and we'll have that semi-orthogonality. And so maybe one very special case of this is when Y is actually a point. Right? Because if Y is a point, then this projective bundle again becomes linear algebra, just a projective space. And then, yeah, we'll just get a semi-orthogonal decomposition of the projective space into derived categories of a point. Right, where the points will be embedded by line bundles. We can take O of 1, etc., O of R. Yeah, this is the famous Beilinson full exceptional collection on the projective space. So I don't want you to have an impression that it's easy to have semi-orthogonal decompositions. So let's talk a little bit about what's known about decomposability of the derived category. Go ahead. Well, I'm not sure I understand the question. Maybe let's talk later about this. Maybe it's something. Or maybe I will actually answer it right away. Did you hear the question?
No. Do I bring the microphone? Did you hear?
No, I didn't hear, but maybe I will answer it right now because so here's a conjecture. It's a well-known conjecture that kind of relates the subject to the minimal model program. So what this says is that if Kx is nef and effective, then the derived category of X is indecomposable. So indecomposability is some kind of version of minimality, if you want. So there are some results in this direction. Right? So for instance, there is a theorem of Kawamata and Kawatani and Okawa that if the base locus of the canonical system is, well, empty or finite, then dB of X is indecomposable. And there is an even stronger theorem of Lin that says that if the what's called the paracanonical base locus is finite, then the same thing is true. So what's the paracanonical base locus? You take the intersection of base loci of canonical class tensored with a topologically trivial line bundle. So here L belongs to peak 0 of X, where by peak 0 of X, I mean the connected component in the Picard group of X. And so if this is finite, then there is the same conclusion. So as an example of the example, what's that? In the first theorem, I'm assuming that the base locus of the canonical linear system is finite. Yeah. Again, smooth projective. All my varieties are smooth projective. Yeah. No, here it literally has to be effective. But could be 0. Like, for example, if you have a, if Kx is trivial, then this is an example of this. And in fact, this kind of goes into this first theorem, right? Because the base locus is going to be trivially empty. Yeah, so like there are no semi-orthogonal decompositions on Calabi-Yau varieties. Okay. And as an example of an example, let's take C to be a smooth projective curve of genus G, and let's look at its symmetric powers, right, which is just a quotient of the product of k copies of C by the symmetric group. So then one can ask, well, if these conditions are satisfied there. In fact, there is a theorem which is due to Biswas, Gomez, and Lee, that if you take a point in the symmetric power, and what's the point in the symmetric power? Well, it's just k points on the curve. Right? And then, this combination is in the base locus of a linear system, of the canonical linear system, if and only if this divisor, P1 plus Pk, has another global section. So basically, if you have, for example, hyperelliptic curve, then this base locus is not going to be finite starting with k equals to 2. Right? And so then I guess what this shows, right, is that if k is less than the gonality of C, right, so then the first theorem by Kawatani and Okawa implies that the derived category of sim Kc is indecomposable. Right? But then the second theorem by Lin actually implies something much stronger. The second theorem implies that if k is just less than the genus of the curve, then Lin implies the same conclusion. So it's much stronger. Even generically, the gonality will be like half of the genus roughly, and this will be true up to G. So the theorem of Lin, because of that, looks much stronger, but in fact the proof is almost the same. So that's why I'm kind of putting them both together on the blackboard. Okay, so how about what happens after that? Well, take for example the Gth symmetric power of the curve. Well, if you take sim G of C, then this has a well-known birational map, just a summation map or the Abel-Jacobi map into peak G of C, right? It's birational, right? And we already know that if we have a birational morphism, then peak G of C must be a block in sim G of C. So the derived category of sim G of C will be decomposable into something, and the derived category of this abelian variety. Yeah, it actually took a while to figure out what the other part of that semi-orthogonal decomposition is. So this is a complicated theorem of Toda that is actually the derived category of the G minus second symmetric power of the curve. So if you know something about Brillouin-Noether loci on peak GC, you know that the G minus second symmetric power of C resolves the Brillouin-Noether locus, the locus in peak GC where this map is not an isomorphism. And so this is somehow like the non-commutative resolution version of that. Okay. Okay, so then another thing I want to point out is that not every admissible subcategory is of geometric type. So here the most famous example is certainly a cubic fourfold. When you take X in P5, a cubic fourfold, right, so then on the Fano variety, the structure sheaf will be an exceptional object. So you can kind of start decomposing the derived category into that structure sheaf. But also the cubic fourfold is a Fano variety of index 3, right? So we can continue a little bit. We can add 2 more line bundles, 2 more points, so to speak, like point type blocks on DBX. And then there is another block that maybe I can call A. And so that's what's called the Kuznetsov component. And so it's not that difficult to see that if A is geometric, if A is a derived category of something, then that something must be a K3 surface. Yeah, but then the problem is that if you look at the moduli space of cubic fourfolds, it has dimension 20, but the moduli space of K3 surfaces has dimension 19, which implies that not every cubic fourfold has a geometric admissible subcategory. Right? So this is typically not geometric. Right, and of course, Kuznetsov has the amazing conjecture about this. That if X is a rational variety, if it's birational to P4, then this admissible subcategory must be geometric. It must be equivalent to the derived category of a K3 surface. And so then, of course, if true, this conjecture would imply that a general cubic fourfold is irrational. Go ahead.
So is the derived category of the K3 surface is not really decomposable?
Derived category of a K3 surface is always indecomposable because it's Calabi-Yau, right? As soon as canonical class is trivial or has a finite base locus, you're done. It's indecomposable. Yeah, good question. Any other questions? Okay, so another question we can ask is what kind of smooth projective varieties can show up as blocks in derived categories of Fano varieties, right? Because from this point of view of canonical classes that I raised, it's the Fano varieties that have the most interesting semi-orthogonal decompositions. But if there is one recurring theme in this conference is that the Fano varieties are the most beautiful, interesting kinds of varieties anyways. So we should kind of focus on those. Right, and so this question is has the amazing and really outrageous conjecture attached to it. So this is called the Fano visitor conjecture due to Bondel, right, which says that if X is a smooth projective variety as always, so for every X, every X is a block, maybe I should say for every X, dBx is a semi-orthogonal block in some Fano variety. It's really amazing if you think about it. Like if you remember from Joaquin's lectures, the class of Fano varieties is bounded. There's only finitely many families of Fano varieties in every dimension. But of course here we're dealing with arbitrary smooth projective varieties. But an easy exercise for you is to show that there are countably many possible families of arbitrary smooth projective varieties. So at least theoretically, it can kind of work, right? But the dimension of that Fano host that will contain arbitrary smooth projective variety will, of course, have to increase dramatically as you go along. So this is known in very few cases. So this is known for symmetric powers of curves. So this is essentially due to a construction of Thaddeus, right? Because the problem is always just to find that Fano host. And Thaddeus found a nice Fano host for symmetric powers. And as we already know, symmetric powers include Jacobian varieties as their blocks. So therefore, also every Jacobian variety shows up in some Fano. It's also known for complete intersections. So which is already a very large class. So this is due to Kim, Lee, and Lee. In which case, one can just construct, again, the Fano host. So there is a construction of a Fano variety starting with a complete intersection. And that Fano variety will contain the original complete intersection as a block. So this is also known for Enriquez surfaces due to Kuznetsov. Yeah, and well, it's also known for now for 75% of K3 surfaces. Right, this is a very new result by Anibal Aravena, who's here. So hopefully by the end of ELGA, he'll get to 100%. That would be great. So the genus shouldn't be 3 modulo 4, I think, current. Yeah. Yeah. And it should also be have Picard group Z, the smallest possible. Okay, so then you kind of start thinking, well, how can you possibly prove the Fano visitor conjecture, right? So how would you actually construct that Fano host in general? And the more I think about it, the more I'm kind of convinced that the only way how this can possibly work is the following, as I call it, crazy conjecture is true. So basically, just start with arbitrary X and then embed it into a projective space by some sufficiently ample line bundle. Right? So then, of course, we all know that the blow-up of the projective space in X is not going to be Fano, but the conjecture is that maybe it is log Fano. Yeah, and in this room, there are many experts on log Fano varieties, so I really hope that by the end of this conference, maybe this will be disproved. But, yeah, so then why is this good? Well, if you are a log Fano variety, then, well, you have a so-called Fano model. So So maybe if we call this Z, right, we can take the approach of global sections of multiples of Kz. Call it the Fano model, right? Which in general, will have singularities, but since we are in this kind of a crazy world, maybe it's smooth. And if this is smooth, then it's actually relatively straightforward to see, I think, that the derived category of X, well, first of all, it will embed into the derived category of Z. Well, that's just a general instance of a so-called Orlov blow-up theorem. Right? Every time you blow up something, the center of the blow-up will show up as an admissible subcategory in the blow-up. So this is the Orlov blow-up. But then it's a bit harder to prove, but it should be true that dB of Z is an admissible subcategory of the derived category of that Fano variety, F. And you're done. You will prove the Fano visitor conjecture. So it's kind of annoying, but again, this is only true in a very few cases. And the problem is that we don't know how to analyze this log Fano, how to prove that it's log Fano using just birational geometry. So we need much more complicated tools for that. And so I think my understanding is that this is currently known essentially for curves. Again, this is due to this is the same construction by Thaddeus. And it's also known for that 75% of K3 surfaces by sort of the same analysis by Annibal. But if it's true for curves, who knows? Maybe it's true in high dimension. Go ahead. Yes, for a sufficiently high embedding. As soon as the polarization has degree at least 2G minus 1, this is true. It have to be sufficiently high, yes. Okay. Right, so now how about, so now since we're in this dream world, so we are dealing with these Fano varieties, or log Fano varieties, but they have Picard number 2. Right? Because you blow up something, so you have Picard number 2. So how about Fano varieties with Picard number 1? That would be even better, right? So how to deal with Fano varieties of Picard number 1? And so let me show you one example when this is actually computed. So these are the moduli spaces that showed up in Davesh talks last week. So again, let's take the same smooth projective curve of genus G. And so now let's take the moduli space of semi-stable rank 2 vector bundles on C. And so in Davesh talk, he wasn't fixing the determinant of a vector bundle, but let's fix that. Let's just fix the determinant to be a fixed line bundle. And the reason why I want to do this is because then it's well known that this moduli space is a Fano variety. It has dimension 3G minus 3. And its Picard group is Z, generated by what's called the theta line bundle. So it looks like it depends on which line bundle you choose, but in fact it doesn't. If you just tensor your vector bundle with an arbitrary line bundle, the determinant will just change by the square of that line bundle. So essentially there are only two cases, odd degree and even degree. And so if the degree is odd, and then it's convenient to actually choose it to be 2G minus 1. So then generically, this vector bundle will be an extension. So that's the great thing about studying vector bundles on curves. They're all extensions of line bundles. So it will be an extension of a trivial line bundle by lambda. And because of that, this variety, Fano variety, is actually rational, right? Because it's just birational to the space of all possible extensions like this. So now if the degree is even, it's a little bit different. So, so this variety is going to be singular if genus is at least 3. It will have rational singularities, being a GIT quotient and all that. And very embarrassingly in algebraic geometry, its rationality is unknown. It has been unknown for like 60 years. So it's a challenge for the new generation to prove that this moduli space is rational. So if you do the same construction with extensions, you will realize that again, one can write down every vector bundle as an extension, but now there are choices. So the space of extensions is a projective space of dimension 3G minus 2, and it dominates the modular space of vector bundles with generic fibers P1, so it's a unirational, but proving rationality proved to be a very kind of a complicated problem. Okay, and so now we can ask, okay, what is the semi-orthogonal decomposition of this moduli space? Right, so there are two cases, so there are two theorems. So in the odd degree, so we have a theorem proved in two papers that this derived category of Fano variety of modular space of this rank 2 vector bundles has a semi-orthogonal decompositions, and the blocks of this semi-orthogonal decomposition are derived categories of these symmetric powers. And the symmetric powers that show up are exactly the ones when k is less than genus. So where we know by Leon's theorem that these guys are indecomposable. So that's like a maximal decomposition. And so we also have a theorem in the even degree, but maybe to save on time, let me not explain what it is, because in this case, one has to do harder work. The moduli space is singular, so one has to work with its resolution of singularities. And so instead, let me sort of add to this web of conjectures one more conjecture. Yeah, but to do it, well, I have to explain a little bit this idea that semi-orthogonal decompositions have mutations. So mutations of SOD. So one simple example is to take the derived category of P2, right, where, as we already know, well, there is this three-term semi-orthogonal decomposition just given by points by this Beilinson collection. And so then what we can do, we can kind of keep two of them the way they are, but then we can change O to the minus canonical class, right? So we can change it to O of 3. And this is a very general thing. One can always just shift semi-orthogonal decomposition by tensoring one of the blocks with the anti-canonical divisor, right? So this gives a new semi-orthogonal decomposition, and one can kind of continue in this fashion, getting this kind of a nice braid on 3 strands. And more generally, well, if you have some semi-orthogonal decomposition of dBx, it will have some pieces in it, and maybe you can take 2 adjacent pieces. And then one can always keep all of the blocks the way they are, move one of them, let's say, to the left, but it's the same block, the same derived category. And then it's guaranteed that there will be a way to mutate one of them to the right. And what will happen is that the result of this mutation will be, as a category, as an abstract triangulate category, it will be isomorphic to AI, but it will have a different embedding into the ambient derived category. And so there are these mutations, and this gives the action of the braid group on R strands on all possible semi-orthogonal decompositions. And if you do it with P2, you will get exactly this Markov tree that Giancarlo described in his talk, right, where you have all these exceptional vector bundles on the projective plane. And so now, so here's, I think, a conjecture which would really clarify what's going on with these semi-orthogonal decompositions. So I call it a two-ray game conjecture. Which says the following. So let's say we have a smooth Fano of Picard number 2, and then like in Cynthia's talk, let's take 2 extremal contractions. So this is Fano, let's say of Picard number 2, and then will be Fano Y and Fano Z, and these guys will have Picard number, let's say 1. And so then the conjecture says that we can do the following. We can take the derived category of Y and find some kind of a semi-orthogonal decomposition for it. And then we can embed the semi-orthogonal decomposition into the derived category of X, which is a rank 2 Fano, but maybe add more blocks. This will be some more blocks, C1, CR. And then one can mutate these blocks by the braid group, so there's some kind of a complicated braid. And you will get a new semi-orthogonal decomposition of the same category. And then what will happen is that the first T blocks from that semi-orthogonal decomposition will sort of reassemble to give us the derived category of Z. Right, so that's a conjecture, right? And because of that, it kind of gives a way to study derived categories of Fano varieties of Picard number 1 by connecting them through this sequence of extremal contractions to some known varieties of Picard number 1, where this semi-orthogonal decomposition is already known. I should also add that the reason why this conjecture is so amazing is because we even know what the braid is going to be. Right? So there is this kind of braiding conjecture that the braid will be the monodromy braid of the quantum spectrum of our rank 2 Fano variety. Right, so so there is this deformation, right, of the cohomology ring of C to what's called the quantum cohomology of C. It's a flat deformation of finite dimensional algebras, and then the usual sort of a cup product will deform into what's called the quantum product, but not just one quantum product, but it will depend on the parameter. And so there is this big quantum cohomology where the parameter is itself an element of the cohomology, but then there is something called the small quantum cohomology when this parameter, I think usually people call it tau, belongs to just H2 of XC. Right? So you get sort of a family of algebras parameterized by essentially your Picard group. And then what's the quantum spectrum? Well, you can take the first Chern class of X, our canonical class, mine's canonical class, and then you just multiply, right? So it will act on the quantum cohomology, right? And you take its eigenvalues. So that's what quantum spectrum is, right? If you have a linear operator on a finite dimensional vector space, you have eigenvalues, and that's what's called a quantum spectrum. And I think I have just enough time to show you an example of this. It probably looks very abstract. But let me give you one example. So let's say the genus of the curve is equal to 2. All right, so in this case, this moduli space of rank 2 vector bundles was computed by Newstead in the 60s. And what it is the intersection of two quadrics in P5. Right. Okay, and so now we have to define a two-ray game, right? So we need to have two extremal contractions. Well, what we can do, we can blow up a line in that intersection of two quadrics, right? And this will be one extremal contraction. But then the same space, so this will be my Fano variety of Picard number 2, but then the same Fano variety can be blown down to P3. It's actually also isomorphic to the blow-up of P3 in my curve embedded by a degree 5 linear system. And so this has a different contraction down to P3. Well, so we know the derived category of P3. It has a Beilinson exceptional collection. And so then this two-ray game conjecture should take this exceptional collection and then somehow convert it into the derived category of the moduli space. So let's see if I can show you that, and that will be the end. Right, so let's start with the quantum spectrum of P3. Right, so P3 has this exceptional collection with 4 line bundles, and the quantum spectrum here is just this kind of a cyclotomic spectrum, plus or minus 1, plus or minus I. And so now we start moving in our moving cone, right? So you can see the movie on my webpage, but here I just have this kind of a picture. So it moves, and then this big guy shows up. And this guy is an eigenspace. Just 1 minute. Yeah. And this eigenspace, yeah, so this is an eigenvalue, but it has an enormous eigenspace given by the cohomology of a curve. And so this big guy shows up, and boom, boom, it tries to overtake one of the eigenvalue. And then if you keep going, they kind of dance around together. And if you really resolve, they really dance. They go like around each other 3 times. Yeah, and then at some point, the curve settles at the origin, and then it kind of kicks away this magenta eigenvalue. And then magenta eigenvalue flies so fast that these 2 guys just go away, and we end up with a much simpler quantum spectrum of the intersection of 2 quadrics, right? So that's the end of that kind of a monodromy braid. Yeah, and if you kind of compute it, well, that's what you get, just kind of a simple braid. And so in the top, you know, we have a Berenson collection on P3, and then we have a derived category of a curve showing up. And then there is this kind of a complicated braid. So here we have this dance around each other 3 times. And then 2 guys fly away, and then only 3 guys are left. And so again, we have a structure sheaf, trivial line bundle on that intersection of 2 quadrics. You know, we have the state aligned bundle. And then we have a sort of a really mysterious copy of the derived category of a curve embedded by the Poincaré vector bundle, by the universal vector bundle on C times the moduli space. But unfortunately, this is only kind of a conjectural, so we can't really prove things this way yet. You know, so what we really do, we sort of work hard and change this braid into that braid. It's the same braid, but drawn very differently. And then we construct these mutations in the derived category using various algebraic tricks. Right, so I will skip that slide because I don't have time for that. Yeah, and so this is then the analogous picture, but in genus 5. You know, when you start with the derived category of the projective space, and then you add a lot of things, and then you do this kind of a complicated braiding apparatus, and then you end up with the derived category of the moduli space of rank 2 vector bundles.